This is part 4 of a series on KNN. In this video, we'll look at weighted KNN, shortly WKNN. This video was produced in Korean and translated into English. The audio was generated by AI, text-to-speech. In the last video, we looked at the curse of dimensionality and lazy learning, and wrote code to perform KNN classification using scikit-learn. In this video, we'll look at different ways to classify test data other than majority voting, and we'll look at weighted KNN, which gives different weights to neighbors. Then we'll write some code to implement a WKNN model from scratch. Additionally, we will also implement the WKNN model using scikit-learn's KNeighborsClassifier. Now let's look at different ways to classify test data other than majority voting. In this situation, should test data point X be classified as red or as blue? This figure shows 8 training data points around the test data point X. These are the candidates to be the nearest neighbors of the test data point. We want to find the 5 nearest neighbors among these. The 3 candidates 1, 2, and 3 are inside this circle. And the other 5 candidates, 4, 5, 6, 7, 8, lie on this circle with a similar distance from the test data point X. For example, these distances are 2.0 plus minus 0.1. But let's assume that all the distances are 2.0. The plus minus 0.1 can be considered a measurement error. The 3 candidates, 1, 2, and 3, can be easily chosen as the neighbors since they are definitely inside the circle. However, choosing 2 neighbors from the remaining 5 candidates, 4, 5, 6, 7, and 8, is not easy, because they are all at the same distance from the test data point. How can we classify this test data point in this situation? We can consider the following 3 methods. The first way is to randomly choose the neighbors. First, choose the data points 1, 2, 3 inside the circle, and then randomly choose 2 out of these 5 data points that lie on the circle. Let's say the data points 4 and 6 are chosen. Then, since red is the majority, this test data point can be classified as red. This method is simple, but the results may vary depending on which data points are chosen. The second way is to classify the data point X into the class that has smaller sum of the distances. This method uses all 8 data points. First, we measure all the distances between the test data point and the red data points. This distance is 1.2, and all other distances are 2.0. Therefore, the sum of these distances is 7.2. Next, we measure all the distances between the test data point and the blue data points. This distance is 1.0, and this distance is 1.3, and the other 2 distances are both 2.0. Then the sum of these distances becomes 6.3. We choose the smaller of the 2. Since this value is smaller, the test data point is classified as blue. The third way is to classify the data point X into the class with larger sum of the selection probabilities. This method also uses all 8 data points. First, we compute the selection probability for each data point. Since the data points 1, 2, and 3 are all inside the circle, their selection probability is 100%. And since we have to choose 2 of the remaining 5 data points, the selection probability is each 2/5. Next, we compute the sum of the selection probabilities for each class. The sum of the selection probabilities for blue is 2.8. And the sum of the selection probabilities for red is 2.2. We choose the larger of the two. The test data point is classified as blue because blue has a larger selection probability. Next, let's look at weighted KNN. Let's look at the following example. In this example, when the value of k is 5, does it make sense to classify the data point X as red or as blue? There are 5 data points within this circle. Reds are the majority, but are slightly further away from the test data point, while blues are the minority, but are close to the test data point. In this situation, we want to predict the class of this test data point, X. In the standard KNN, this test data point would be classified as red, which is the majority. All neighbors have equal weight. This is simply decided by majority voting without taking into account the fact that this test data point is closer to blue. Next, let's consider how to give higher weights to data points that are closer to the test data point. This is called weighted KNN. The closer the distance, the higher the weight. The weight is inversely proportional to the distance. Therefore, the weight can be simply defined as the reciprocal of the distance. The distances between the test data point and the 5 training data points are as follows. And the inverse of these distances are as follows. Their sum is 3.65. Next, we compute the weights of the inverse distance for each class. The inverse distances for the blue class are 1.25 and 0.67. Then the weight of the blue class becomes 0.525. This can be interpreted to mean that there is a 52.5% probability that the test data point belongs to the blue class. The weight of the blue class is 0.475. We choose the larger of the two. Then this test data point will be classified as blue. Since the data point X is closer to blue, it might make more sense to classify that point as blue. This is weighted KNN. Next, let's implement weighted KNN in code. To simplify the problem, let's assume that a distance matrix is already given as follows. There are 5 test data points and 10 training data points. So the distance matrix has 5 rows and 10 columns. For example, the distance between the first test data point and the second training data point is 3.5. And the distance between the third test data point and the first training data point is 4.6. And let's say the classes of this training data are as follows. The class Y is either 0 or 1. The value of K is set to 7. T is the number of test data points, which is 5. First, as we did in the first video of this series, we find the K nearest neighbors to the test data. I near and Y near are 5 by 7 matrices respectively as follows. These are the indices of the training data points that are close to the test data. The first row contains the indices of the 7 training data points closest to the first test data point. And the second row contains the indices of the 7 training data points closest to the second test data point. The first element indicates that training data point 4 is closest to the first test data point. The distance is 1.4, which is the smallest value in the first row of the distance matrix. And Y near contains the classes assigned to the training data points above. The training data point 4 has class 1. And the training data point 9 has class 0. Next, we compute the inverse distance. First, we obtain the distances of the training data points contained in I near from the distance matrix. This is the matrix WDist as follows. And find the inverse of these distances. This is the matrix WNV as follows. Now, let's use this matrix to predict the class of the first test data point. Compute the weight of class 0 for the first test data point. The result is 0.38. As mentioned earlier, this can be thought of as the probability that the first test data point belongs to class 0. And compute the weight of class 1. The result is 0.62. Since this value is larger, the first test data point is classified as class 1. The code on the left performs this process for every test data point. The predicted classes for the test data are as follows. Let's compare the prediction results of the standard KNN and weighted KNN. Since the standard KNN uses majority voting to determine the class of the test data, the prediction results will be as follows. However, weighted KNN classifies the test data as follows, as we just saw. The predictions for the fourth test data point do not match. Standard KNN classifies this as class 1. But weighted KNN classifies this as class 0. Although class 1 is the majority, this test data point is closer to class 0, so WKNN classified it as class 0. Next, let's implement a WKNN model to classify the iris dataset. Load the iris dataset. Since it is similar to the code we used before, we will only look at the part that implements WKNN. First, we compute the distance matrix between the test data and the training data. Second, find the K nearest neighbors of each test data point. This code is identical to what we looked at on the previous page. Third, we compute the inverse distance. Fourth, we predict the class of the test data using the weights of the inverse distance. Finally, we measure the accuracy on the test data. YPRED1 contains the classes of the test data predicted by this method. The accuracy is 0.974. Next, let's implement the WKNN model using scikit-learn. And let's compare the results with those on the previous page. We will use scikit-learn's KNeighborsClassifier. Setting the weights argument to distance creates a WKNN model. This will do the same thing we did on the previous page. Fit this model to the training data, and then predict the class of the test data. YPRED2 contains the classes of the test data predicted by scikit-learn. The accuracy on the test data is 0.974, the same as that of the previous page. Next, let's compare the YPRED1 and the YPRED2. The two results agree well. Let's run this code. We got the following results. So far, we've looked at different ways to classify test data, and we've also looked at weighted KNN. In the next video, we'll look at how KNN handles categorical features.